In this video, we're going to cover friction. We'll talk about static versus kinetic friction. We'll go over centripetal force and the momentum principle again briefly. And we'll apply these to two problems. And so one of them has to do with some boxes being pushed, and the other one has to do pretty much with a wrecking ball or Tarzan swinging on a rope. So starting with force, we've gone through this a couple times now, but we got four fundamental forces of nature. We got the Newton's three laws of motion, and then we have these different formulas that we've learned for forces. The two that we are concerned with today is having to do with friction, and then also the centripetal force. And so starting with static and kinetic friction, what we want to understand is that when we first start pushing on our box, let's say, with an applied force, we're going to experience some resistance, but the box is not quite moving yet, and so we're applying a force, but we're not overcoming friction yet, and that's called static friction. There's no motion between the two surfaces, and so the force of static friction is just going to be equal to your applied force up until this threshold of motion. And at that point, it's going to break loose and start moving. And at that maximum point, we actually have a formula with the coefficient of static friction, which can be determined experimentally between two surfaces, two materials, times the normal force. And so at that threshold, it breaks down into kinetic friction, which it's easier to slide an object than it is to get it to start moving. And so notice how that coefficient is less. And at that point it remains relatively constant. And so for kinetic friction, when these two surfaces are in motion relative to each other, we can pretty much always just use this coefficient of kinetic friction times the normal force formula. Whereas up here, we can only use this formula at the maximum, and we know that it's equal to the applied force up until and including that maximum, and then it breaks. Okay, and so another thing to consider is we have these different materials, and we can define coefficients for these different materials, and notice how the static friction coefficient is always greater than the kinetic, and so it's harder to get things to start to move than it is to keep them in motion. And another thing to consider is what's happening at the molecular level, and so we have these atomic and molecular interactions between these two materials. You may have heard that two things never really touch because at the molecular level, at the atomic level, we have just this repulsion of electrons when you try to get really, really close to touch something. And so we basically have this interaction here. And then once it starts sliding, you can imagine that those interactions are not as strong. And so that's one way to view friction at the molecular level. Another thing to consider is our kinematic formulas that we learned before, and we had 5 of them. We can also look at them in their angular form. And so when we have angular motion in a circle or just in an arc or something like that, we can look at what's going on with basically defining a radius to that arc. And so notice how these equations 1 through 5 kind of translate over. And so instead of acceleration, we have angular acceleration. Instead of displacement, we have angular displacement. Instead of velocity, we have angular velocity, and so on. Time pretty much remains the same between the two. We also are dealing with angles now, and so we're talking about revolutions, degrees, radians. We have this idea of arc length, and if you go all the way around, you get to the circumference, which is 2 pi r, and we have a time period, which is the time it takes to go all the way around. And then we have some other formulas here which look pretty similar to what we've learned with linear stuff. We look at the units, and instead of talking about meters, we're talking about radians. Instead of meters per second, a lot of times we do radians per second, and so on. And so we'll also eventually talk more about angular force, which is torque, and angular mass kind of, or angular inertia is this moment of inertia, and angular momentum. And so basically talking about these quantities, these linear quantities in terms of their angular version. And so that's something to keep in mind as we move forward, especially with that wrecking ball problem. And so we have to talk about centripetal force if we're talking about angular or circular motion. And so we recall that acceleration is just the derivative of the velocity pretty much with respect to time, but we can usually just write it as delta v over delta t, and then we remember that velocity is just displacement over time. And so we can imagine we have a circle here with a center, and that's basically the definition of a circle, is pretty much the collection of all points equidistant from a center point. And so we can imagine we're starting at some initial position, let's say 90 degrees relative to this 0 degree reference, and we can imagine that we're traveling at some initial velocity which is tangent. Let's imagine you're swinging something around in a circle, and so that is at 0 degrees, if you can imagine that. And then we have a final position at some later point in time, and we've had some angular displacement now, and so we're at some new angle. And so this angle we could say is 60 degrees. We could view this as 30, 60, and 90. And so that's going to have potentially a new velocity, or maybe the same, but we have some final velocity, right? And so that is directed at 30 degrees below the horizontal, so negative 30. And so what we could imagine is we have this angle here between our initial position and our final position, and we can look at that angle by basically just doing 90 minus 60. To get 30, and so we kind of know that that's going to be a 30 degree angle for this example. We're just plugging in numbers as an example here to make it a little easier. And then we could also look at how to get to that angle from up here, and so we could say, okay, well, we got 0 minus a negative 30. That angle between there is also going to be 30. And so the reason why we did that is so that we can kind of take these vectors, and with the principle of superposition we can kind of move these vectors and around in space and look at what's going on. And so we have some change in velocity potentially here, and we have this idea that the magnitude is the same. And so let's just make that assumption, that we're basically not changing our speed. We are changing direction though, and so because we're changing our direction, and since velocity is a vector quantity, we actually are changing our velocity, but we're not changing the magnitude of our velocity. So this is an example where we're only changing our direction. And so let's just assume that we're at the same speed, so we can look at what's going on due to changes in direction only. And so let's assume that our initial and our final are pretty much the same, and so we'll just call that v. And then let's look at our position, and we have some displacement here, initial to final, and we can basically say that that's the same in terms of magnitude as well, because it's the radius of a circle, and so those magnitudes will be the same because it's the radius. And now we can use this idea of isosceles triangles, which means they have two sides of equal lengths and we have the same angle, and we can set up a proportion, which is basically setting two ratios equal to each other, and so the ratio of the bases equals the ratio of the sides. And we end up with this expression here, where we can say that the change in velocity over the velocity equals the change in position over position, pretty much. And so we take that expression and we can do some work with it here and just see what we get for this new idea of acceleration. And so what we'll do is we'll divide both sides by time. That's totally fine. We can, as long as we do the same thing to both sides of the equation algebraically, and it should be okay, right? And so we'll divide both sides by time, and we'll just kind of see what happens here. And notice how this change of velocity over time looks very similar to the acceleration, and we have this change in position over time looking very similar to just the velocity. What we can do is view this change in velocity over time as just the centripetal acceleration, this new acceleration that is only coming from changes in direction, and then we can plug in just v for the delta r over delta t. And so you'll notice how we can multiply both sides by v to get rid of it on this side, and we'll solve for that centripetal acceleration. And we get the centripetal acceleration is v squared over r, which a lot of times is told to students just to kind of memorize, and it's not really shown where it comes from. And so this is one way to think about where it comes from, and it's basically just saying that there's some acceleration due to change in velocity, right? So, but it's not due to magnitude changes, it's due to direction changes. And so that leads to this new idea of a force, which is called centripetal force, which is mass times that new type of acceleration that we have. And so we could also write it as mv squared over r. And this centripetal force is a kind of a new type of net force, looking at what's going on to hold or oppose something in circular motion. And so we have some formulas up here, and a lot of times we're setting it equal to what supplies it. And so a lot of times it's supplied by tension if you're swinging like a yo-yo around in a circle or something, or friction if you're turning on the road, or normal force on like a roller coaster loop, or even gravity if we're talking about some planetary motion or something, or satellites or something like that. And so the other thing to point out is that velocity is just equal to angular velocity times radius. And so radius is really the way that you can convert between angular and linear. We might get more into that later when it's a little bit more important to the problems at hand. But today it's mainly just the centripetal force is mv squared over r. And so hopefully that makes sense where that comes from now. And the other thing to mention is that we considered that this was uniform circular motion, so it was a constant speed, because we didn't want to add that additional complication. And so it kind of looked like this, where the magnitude was not changing, but the direction was. And so this centripetal acceleration and also centripetal force is always pointed towards the center of the circle. It's trying to hold it into circular motion. But if we have some non-uniform circular motion, so imagine that you are spinning something and then you're spinning it faster and faster and faster, we also have some angular acceleration. And so we have, this tangential acceleration here, and we have the centripetal acceleration, which can combine together to give you a total acceleration. You can use the Pythagorean theorem to figure out what that is in terms of magnitude, and we could find the direction as well. And so that's the difference between uniform circular motion and non-uniform circular motion. Okay, and then momentum and impulse, we understand what momentum is, mass times velocity. Impulse is any time the momentum changes, and we have assumptions that are a lot of times made where the net force is constant, or acceleration is constant, especially over a small interval. And if you have a small enough interval, you basically get into calculus. And so we have this idea of updating our momentum and updating our position. And we have this momentum update and momentum principle and our position update that we've talked about. But the key thing for today is really just understanding the idea of net force. And it does connect to momentum, but we want to understand that the net force is basically the sum of all the forces. And so we'll get into that here with this problem. And so with this problem, we have boxes on top of each other. And we have a force acting on it. And so what we'll do is we'll say, okay, well, if this system is being pushed, we must have some friction holding the two boxes together. But it does say that there are there's no friction pretty much on the bottom here. So it's being pushed in like an ice rink. And so there's no friction here, but there is going to be friction between the two boxes. Otherwise, the top box would just slide right off, right? So the only thing that's really pushing this bottom box forward is the frictional force from the top box. And the frictional force from the bottom box is kind of holding that top box back a little bit. And so that's one way to think about it. And so what we need to do is draw a little bit more information here with the free body diagram. And we understand that there's a normal force on the bottom box, and also on the top box. You can kind of look at the system as a whole, but then you can also look at each box individually. And so we're not as concerned about the normal force of the bottom box. It is going to have the extra weight of the top box on top of it, but there's no friction here on the bottom surface, so we don't care as much about that. We're mainly concerned with the normal force here on this box, which is basically just equal to little mg, the gravity acting down. And the applied force is only on the top box. And so we're going to use the momentum principle, the idea of net force. We're going to assume that there's no significant frictional force on the lower box between that and the ice. And we're going to assume that we don't need to consider aerodynamic drag. And we're definitely not going to consider relativistic effects. And we are going to identify to start off with that the system can be both of our boxes, and that'll help us determine the acceleration of both boxes, because if this system is accelerating, that means the acceleration of the top box has to be equal to the acceleration of the bottom box, as long as there's no slippage here, and so that the whole thing is accelerating as one unit. And so we'll solve the problem. And the first thing that we can instantly do pretty much is conceptually understand that the directional the direction of the friction force on the top box due to the bottom box is going to be to the left. And so we kind of talked about that a little bit already, but we'll mention that again here in a second. But we want to figure out what is the magnitude of that frictional force. And so what we'll do is we'll take a look at some of these bullet points here, and it'll kind of guide you through some of the concepts. But the general idea is that we understand that we can set up our net force for both blocks, and we can view it as M plus M, so it's the whole system. And the only force that we really need to consider acting on the whole system is the applied force acting to the right. And so we can look at this in terms of magnitudes, and we're only really looking at the x direction because that's where the motion's happening, and the y direction is just going to give us information about our normal force and gravity. And so we know the system is accelerating to the right due to the applied force on the top box, and there's no slippage in this first part. And so we know that this acceleration, the x, is just the applied force over m plus m. And so that's an awesome equation that we get from looking at both blocks. We don't actually get friction at all, so that doesn't help us yet, because we actually are trying to solve for friction. And so we got to look at the top box and the bottom box. And so we actually don't have to look at the top box right away, but we'll see that. But if we look at the top box, we're basically, we have a force to the right, which is the applied force, and we have a force to the left, which is that magnitude of the frictional force. Just understand that these frictional forces are in opposite directions, but they're equal in magnitude. And so we'll just look at magnitudes and make it a little easier, and we'll use our negatives and positives to indicate direction. And so we know that this AX is the same because there's no slippage, and so we could plug this into that equation. But we'll actually look at the bottom box first. And so the bottom box is fairly easy because it's literally only experiencing one force. The only reason why it's moving at all is because of that frictional force from the top box. And so we have this big M, and then this AX is the same as over here. And so we can kind of pick where we want to plug things in. But I think one of the easiest ways to do it is just plug it into the bottom box equation. And when you do that, you get a nice equation here for our frictional force. And so that's our magnitude of our frictional force, and we know that direction is to the left. And so that's part one. So part two, we're going to kind of continue on with this idea, and we're going to say, okay, well, this is our formula for before, but we know now that the friction is not just equal to the applied force formula anymore. Like we also can invoke that other formula, and so we're at this maximum point. And so what is the largest magnitude of the force? When they use the words like that, they're indicating that you're at that threshold of motion. And so now we can set it equal to the coefficient of static friction times the normal force. And we understand that the normal force that we care about is the one from the top box, so we're just going to set that equal to mg. And so when we do this, we can solve for the applied force. And so now we get that maximum applied force that we can apply before it starts slipping. And then the part B of part two here, we want to find the acceleration of each box. And so once there's slippage, there's still going to be friction. It's just kinetic friction now, right? And so the surfaces are sliding, and eventually the top box will, the boxes will most likely separate at some point, right? But for now, we're just considering these still in contact with each other, but they are slipping and they are in motion with respect to one another. And so what we need to do now is take a look at our top box, and we're basically trying to solve for the acceleration. The accelerations are not going to be equal anymore like they were before because there is slippage, and so we have different masses, so we're going to have different accelerations. And so we can just take a look at our top box equation, and we'll set that frictional force equal to the mu k mg. Notice how it's the coefficient of kinetic friction this time, and then we can solve for the acceleration of that top box. And it's not going to be the same as the bottom box, and so we do the same thing for the bottom box, and we basically get a different formula here. And so that's a nice way where we can figure out, just easily plug in, is if we had numbers. I know sometimes it's hard to follow if there's not numbers, but no, we could plug in numbers and find that those accelerations are not the same, and we could find that what that maximum applied force is. And so hopefully this problem, understanding that you can kind of view it as a whole system and then two separate systems, and understanding what's happening with friction, static versus kinetic, Hopefully that makes a little bit more sense now after looking at this problem. And so we'll go on to this next problem. And this is where that centripetal force really comes in. And so we have a child swinging, and it could be a Tarzan, it could be a wrecking ball. The idea is that you have something swinging, or pendulum, whatever. And so at the bottom of the swing, they're giving you that the velocity is horizontal, and they're giving you some actual numbers here so we can start to plug in. And so one of the first things that we should do is try to illustrate this. And so we have a kind of circular or partially circular motion here, and we have some radius, which is basically the length of the string here, or cord. And at the bottom is really interesting. So you can look at it anywhere, but at the bottom it's a nice little point to look at, because it's going to be the maximum velocity. And so just if you think about it, let's just assume that this person didn't start with any velocity, and then all of a sudden swinging down to the bottom, it's going to be the most velocity, and then swinging back up, eventually it's going to come to stop again. And so it's kind of this oscillation back and forth. But looking at the bottom, we have gravity acting down and the tension's acting straight up. And so gravity's acting down really the whole time, but in this scenario, and this tension is acting towards the center of the circle the whole time. But at this bottom point, it's a nice little point to look at. And so what we'll do is we'll answer these questions one at a time. And so for part A, we want to look at the parallel component of the rate of change of momentum. And so a lot of times we use the words parallel to represent the direction of motion, and then perpendicular to that a lot of times is directed towards the center of the circle. And so for part A, we are going to just basically say, okay, there's no net force in this direction. The only forces are up and down. And so the rate of change of momentum here, the derivative of the momentum, is pretty much just going to be 0. For part B, we're looking at the perpendicular component. And so for this one, we also are going to assume that we're much less than the speed of light in terms of our velocity, and so the gamma is about 1. But the point here is that we're looking basically at centripetal force like we saw earlier, and we're using that mv squared over r formula, and we're basically looking at, hey, the rate of change of the child's momentum in that direction is basically calculated using that formula. And so we plug in the mass of 26, the velocity of 12, and we plug in the length of the cord, which is 4.3, and so we get 871 newtons. And so for part C, we're looking at the net force acting on the child. Well, that's pretty much going to be the same thing, and so we can kind of think about it as we need 871 newtons in order to stay in this circular motion. And so we must have the force of tension supplying that. However, gravity is resisting you, and so force of tension has to work a little bit harder. And so for part D, we're going to find out how much harder it has to work. And so for part D, we know that the tension's in the upward direction, the gravity's in the downward direction. We're basically adding those two together, and when we take into account the direction, we're going to have this 871 newtons, which we need, but we know we're being resisted by gravity, so we have to add on an additional amount for that tension. And so we got 1,126 newtons for our tension, and in order to supply that force that's needed for circular motion. And so the last little part here, we're assuming that we have this elastic cord, and we can see that at the instant it's at 4.3, but we know the relaxed length in this case is 4.22, and so we can use our formula, Hooke's law, and so we can multiply Ks is equal to the tension, but we're actually solving for K here, and so when we do that division, we got K is equal to 1.4 times 10 to the 4th Newton per meter. And so hopefully this shines some light on how to do centripetal force problems. We also talked about a multiple block system with friction, and how static friction can break into kinetic friction, and how to calculate those coefficients and so on. And so this will pretty much be the last video directly on that momentum principle. And we're going to be moving into the energy principle very shortly. And so we'll see you in the next one.